Bismillahirrahmanirrahim. uh, Today we will start with the seventh chapter. But before we start with the seventh chapter, a small point that was left in the sixth chapter. Yes, if someone has any question, he can ask. So actually, the course is still section 6.2, and 6.3 is actually not in the course. I've also verified with Dr. Mohammad Tahir. But I just wanted to discuss this section because I think it is important from industrial perspectives, just for your general knowledge and its importance. So we have studied various analog systems, and this will be the last subsection where we'll be studying analog. From then on, we will be concentrating our attention to digital systems. So analog systems, we have studied that they are basically amplitude or angle modulation systems, and there were various systems that we had studied. Now, how can we compare these systems? Which system is best for different types of industrial applications? So here there is a comparison based on three perspectives or based on three criteria. So first criteria is the bandwidth efficiency, which system requires the least bandwidth. Then you have the power efficiency, which system requires less power for a given for transmitting a given signal. And lastly is which system has an easier electronics to implement its transmitter and receiver, or ease of implementation. So with respect to bandwidth efficiency, you all know, we have seen that single sideband systems, especially single sideband suppressed carrier systems, which we studied, upper or lower sideband, they require only W bandwidth. So those applications where you have very critical bandwidth requirement, you cannot apply a lot of bandwidth. So there you will be adopting single sideband with suppressed carrier. But the problem with single sideband suppressed carrier, if you could remember, it just takes half of once the signal is modulated. The actual bandwidth is 2W, but we just take half of that, 0 to W. All right. But actually there cannot be an ideal filter that take from 0 to W. Some of the components will be deleted around 0, or from FC to FC plus W components at 0, which now come at FC. Some of them will not be transmitted because of filter limitations. So in those cases, it is good that you can send vestigial sideband. So vestigial sideband, it sends the upper sideband, but also a very small portion of the lower sideband. So in that way, your DC values will also be transmitted. So sound signals, SSB is best, but for video signals, because they have a portion of their signals Fourier transform, a portion of that exists around 0, so it will be useful, especially for image signals, video signals. That is why we will be using VSB. So VSB is used in TV broadcast. And yes, PM and FM, they are not favorable because we have just seen that their bandwidth is 2 beta plus 1 to W, so their bandwidth is very large, so it is not it cannot be justified for bandwidth efficient system. But if you have a very high requirement of very high fidelity or transmission or quality, very less noise, then you might be able to justify the usage of PM and FM. Okay. Because of their good noise immunity. Second criteria is power efficiency, which system has the low power, and we have just seen that FM systems are the best because if you are changing power, you just changes the power of the carrier. Inside all the message signal is in the phase of the carrier. Okay, so if you want to increase the synchronous ratio, actually you will be decreasing the noise power. All right, so this we have all seen. So that is why they are quite power efficient in case of AM systems. Uh, uh, we have uh, yes, we have many systems, especially those without the carrier will be preferred. But with the carriers, they are the least efficient. But they are actually used for having a very simple transmitter receiver um, electronics. But for power efficiency, we can very well see that FM stands out um, because of the properties that we have studied in the previous lectures. On the simplest receiver structure or the simplest electronics, again we have seen conventional AM, or we have a digital sideband. These are uh, relatively simple, and also FM. Uh, so these systems, they are used for broadcast, but you won't be using these suppressed carrier systems, because in suppressed carriers you can very well see that the problem is that you will be requiring more complexity, because you will have to basically regenerate the carrier. All right. By a phase lock loop, or you have to have an oscillator, or you might send a pilot signal, so that will increase the cost of the receiver structure. It will become more complicated or more expensive. So you can see that suppressed carriers, they have the same complexity with respect to the receiver structure, but single sideband is a little bit more complex because of the Hilbert transform requirement. But overall you can see that SSB is still better because it requires half the bandwidth as compared to DSB suppressed carrier. So we will again prefer single sideband suppressed carrier. So this was just an overview of the various analog communication techniques that we have studied in the past. So we are now turning a new leaf in our course, and that is that we are now going to digital systems. Someone has any question with the previous analog part, you can ask before we move on further. All right, so we have studied communication, and then we have seen analog communication. So why do we want to go to digital? So there are many advantages, and some of them are given here. So they have large noise immunity, they have bandwidth power trade-off that was not possible for all the analog modulation systems. You have anti-jamming techniques, cryptographic possibility. Then the most important, that you can use large scale integration circuits, and you can then apply a large amount of digital signal processing techniques to optimize your solution. So these are the various advantages of going digital. So first of all, we have to study in this chapter how we are able to convert, and we would like to convert with minimum distortion. And after conversion, we will be just getting a digital output, that is a stream of bits, 1 zeros, or whatever the values you just have discrete outputs at discrete time. That will be the goal. So there are 3 steps. First step is that you take the analog signal. You first have to sample it. Then, you know, after sampling, you will have infinite values. So you round those infinite values and then they become quantized values. So first you sample in time, you quantize in time, you fix in time, then actually you quantize in amplitudes. So you have fixed amplitudes, and then you can represent these fixed amplitudes by some encoder. Okay, and let us say if I have 256 different quantization levels, so I can very well use 2 to the power 8 or 8 different bits. So for every 256, every level for among the 256 levels, you can represent that by 8 bits, and those 8 bits will be just zeros and ones. So you have actually encoded an analog signal in terms of a sequence of zeros and ones. So sampling, it actually interconnects the digital and the analog world, and it also provides actually sampling is governed by the sampling theorem. So we are actually studying its advantages, or the advantages of sampling theorem. So it also gives us a very clear understanding of how the sampled signal is related to its analog part in the frequency domain, and the time domain is could be easily understood. Haji, let us ask some question here to get an idea. Haji Salman Sahab, are you present? Salman Jameel, are you there? Achha, roll number 144, can you hear me?
Yes,
Roll
sir.
number 1. Achha. Have you studied sampling in other courses, especially in DSP?
Sir, we are studying now in DSP course sampling.
Achha, you are studying now. All right.
Yes.
All right. So I thought that you would have studied, so no problem. So let us go into detail here. Maybe part of it you have studied, but as you have seen in our previous uh, lectures, we will go through its rigorous mathematical interpretation, as well as its conceptual interpretation, so that we are well versed of applying sampling theory, not sampling theorem, not only at the theoretical level but also at the practical level. So I am also grateful to Dr. Mohammed Tahir, who has provided me his notes, where you can also see the practical side of sampling. Theoretical side you can read in the book, or you can see my lectures, and that could be understood. But another thing is the practical implementation, and that comes with experience of transforming analog signals to the digital domain. So some of the insights will also be shared um, uh, of the practical reality. All right, so sampling theorem. What is the sampling theorem? It is quite intuitive, quite logical, simple. But if I have two signals, let us say x1 and x2, one signal is x2, other signal is x1, and you can see here that x2 is comparatively uh, fast changing signal with time, and this is a slowly varying signal. All right, so this is a slowly varying signal. So if I want to sample, sample, you just take the values of the signal at fixed times. So if I want to sample my signal intuitively, you can see here that here I can have large sample intervals because the signal is not changing drastically. But here I will need small samples, the small sampling intervals, so that I can capture the the fast varying time domain signal. So sampling interval depends on the nature of your signal, and in other words you can say that if I write the signal in terms of its frequency domain, so the highest frequency component present in my signal, that will determine the sampling interval, or you can say the sampling frequency. This is all written here, that sampling interval for the signals of smaller bandwidth, they have smaller bandwidth, they don't have high frequency signals. So if they have smaller bandwidth, they have slowly varying, they have less frequencies or low frequencies, so the signal will be slowly varying, and hence you can have larger sampling interval. So a sampling theorem has basically two facts. The first fact is that if the signal is band limited to W, so you can see the meaning of this term is that the signal is band limited to W. It just goes from 0 to W, positive frequency. So we know if it is a real signal, it will also have its negative frequency. So it will be actually from minus W to W, whereas bandwidth will be from 0 to W. So it is band limited, means all the signal energy lies in this frequency band. There are no frequency components outside W. So if this is the case, that signal is band limited to W, from minus W to plus W, and the spectrum is 0 for all frequencies greater than or equal to W, then in that case it will be sufficient that our sampling interval is 1 over 2W. Alright, so we will be going through its proof, but here we just want to visualize. Okay? Remember that thumb's rule, as we saw in electromagnetics, various thumb rules are defined, and we know that those thumb rules have their mathematical grounds, but in the practical world you first of all have to know these thumb rules with their conceptual background. Yes, it is good to have that, but once you know the thumb rules, you are good for industry. You can very well see the applications or solve the problems that arise in system maintenance. So the thumb is that it will be sufficient that if my sampling interval is equal to 1 over 2W. All right. Now, why is this so? You can very well see that yes, TS2W is sufficient. All right. And we will be seeing that actually what is happening by sampling, you are actually replicating. Once you sample the signal, you actually replicate the spectrum infinitely. Okay, and every other spectrum is present at the sampling frequency. So you know, if TS is equal to 1 over 2W, then the sampling frequency, which is equal to 1 over TS, will become equal to 2W. So you are putting another sample at 2W, another sample will come at 4W, and so on and so forth. Similarly, another sample will come at minus W, minus 4W, and so on and so forth. Okay, if its replica comes at 2W, and you know that this was going 0 at W, so this will also go 0 at W, this replica. So there will be no interference, or you can actually see there will be no aliasing. All right, that is why TS is equal to 1 over 2W is sufficient. But generally we have sampling interval less than or equal to 1 over equal to 2W is also good, but it is better to have TS less than 1 over 2W, or we can say that generally we have TS less than or equal to 1 over 2W, or you can say 2W is less than 1 over TS, and you know 1 over TS is Fs. So very well you can say that Fs, the sampling frequency, must be double the bandwidth of the bandwidth of your message signal or your modulating signal, or you could say your your low pass signal or analog signal. So analog signal is in its baseband form, then its sample frequency has to be double its bandwidth, remembering that the bandwidth is a set of positive frequencies for my baseband signal. Haji, is everyone understanding?
Yes, sir.
Perfect. Thank you. Now let us go back to the book. So my concept is that we covered the book, but if there are some things which need to be extrapolated or explained, then I come to my notes. But if there are something missing, then again we will go to the notes. So we will be also using that today. First thing is sampling. But sampling theorem also covers reconstruction. So once you have sampled the signal, now it is in sampled form. All right. So for example, now you just have these samples like this, these dots only. In between, you won't have the signal value. Similarly, here you will just have these values. In between, the signal has all vanished. So how can you get back your signal? Let us say I want to reconstruct my signal, get back my original signal. So you have to use interpolation between these 2 points, this point and this point, and so on and so forth. So you might use linear interpolation, or you might use other types of interpolation, but there are also more sophisticated interpolation techniques. But whatever, by using various interpolation mechanism, for example using a sync, you can get back your original signal. It must satisfy this condition: the sampling frequency is greater than or equal to 2 times the bandwidth, or in other words, you can say the sampling time interval is less than or equal to 1 over 2w, or you can say yes, 1 over 2w, where w again is the bandwidth. The same thing which this or this, these two conditions need to be satisfied. Then you can have various interpolation mechanisms, techniques, and they can give you back the signal. So sample theorem gives us both uh, the both concepts. One concept is how to reconstruct, and the other concept is the bond on the sampling interval, which we just saw. The TS has to be less than or equal to 1 over 2w. Now let us see the sampling theorem with its full mathematical representation. So again, we have a signal x of t, and assuming that its bandwidth is 0 after w, hence its bandwidth is w. So it is 0 for all frequencies equal to or greater than w, which is band limiter signal up to w, and we sample the signal. We sample the signal at ts, where ts we have just seen it has to be less than or equal to 1 over 2w, or fs has to be greater than or equal to 2w. Then you will get a sequence of samples, and that sequence will be at every other ts, interval multiple ts. So at every other sampling time you will just sample the signal and you will be getting the output. You will just take the output of the signal at that sampling time. Let us say 1 ts, 2 ts, 3 ts, 4. वो जो डिजिटल रिप्रेजेंटेशन में आप लिखते हैं ना x of n, तो ना x of 1, x of 2, तो वो एक्चुअली क्या मतलब है? फर्स्ट सैम्पलिंग स्लॉट. सेकंड n means 1 ts, n is equal to 1 means 1, n is equal to 100 means 100 ts. So at every integral multiple of ts you are just getting the signal value, and that is the sampling. Now from that sampling, how can you reconstruct your original signal? So if I want to have sample signal, let us say I go at the receiver and the person saying I don't want these samples, I want to hear my original signal. what I have spoken. Actually, what I am speaking right now, it is going digitally. Nowadays, all our optical fibers and links are digital. So actually, all of it is being converted. But at your end, those digital signals are finally being reconstructed so that you can hear my analog voice. You do not want to hear my digital voice, okay, which it is rounded in amplitude as well it is quantized in time or fixed in time or sampled in time. You don't want to hear that noise, that signal. You want to hear my original speech. Okay, so that is why we will be also interested in reconstruction. The reconstruction formula is given as follows. Uh, so we multiply the sampled signal with this sink, in the shifted sink. We will be seeing its proof also, and then summing this up. So summing this product, and so you will get back the original signal. So here you will be inquiring about this W dash. So this W dash, actually we will be seeing, it actually comes from the bandwidth of the reconstruction filter. So you will be passing this signal, you will see in a while. For reconstruction, we have to pass it through a low pass filter. So W dash actually defines the bandwidth of that filter. We'll be seeing in detail, and that W dash will come out to be as follows. It has to be greater than W, but at the same time it has to be less than this value, which is 1 over Ts minus W. So I would like to, before we go into the proof and all that rigorous mathematical proof, I just wanted to explain this so that we also get a thumbs rule idea for our industrial application. So actually what is happening, this was the spectrum of your sampled signals. It has the original spectrum as well as its replicas. So now I pass it through this filter. Okay, this low pass filter of bandwidth is W dash, but actual width is 2W dash, because W dash is from negative and W dash comes from positive. For example, you can see here, this was your original signal. So I sampled it. Here you can see my sampling frequency is 4W. All right. So the replica will exist around 4W. All right. Next will exist at 8W. Similarly here it will be minus 4W, and let us say the next will be minus 8W, and so on and so forth. We have now. अच्छा, ये तो फिर अभी हमने पढ़ा नहीं है, पहले से आ गया. चलें, just for sake of your understanding, now you can see here that 4W is your sampling frequency. All right, so this W dash, if you could see here, is between W and 1 over Ts minus W. So this W dash is somewhere between W, and this is this is 1 over Ts, and this is W. This point is actually 1 over Ts minus W. This point, because this is 1 over Ts, this is this width is W. This will be actually 1 over Ts minus W, this point. So between W and 1 over Ts minus W, your W dash will lie. Actually, W dash defines, as I just told you, the bandwidth of your reconstruction filter. So reconstruction filter will have its width somewhere here, in between these two, so that you can get back the original signal. This is the spectrum. You just take the signal around this. You just get from this spectrum. You just get back the original, baseband, original message, or original signal is just taken out from the reconstruction of the low pass filter. All right. So all the replicas, they vanish, and you get back the original signal. So other than the mathematical rigor proofs, this is the intuition that actually your after sampling your spectrum is replicated at sampling frequencies. Okay, all right, and by appropriately choosing the original message signal, it could be like this box which chooses this. Here I've made this box. It could be this box, but the condition is the box should get only the baseband signals, the original signal. It must not get the replicas. So there is a distance between those these replicas and this. So you can put your filter here somewhere here, and you can get back your original, original signal from this sampled signal. Okay, and this is the actual intuition, and this intuition can actually conceptually it can be understood only in the frequency domain. Okay, that you pass your sampled or your you can say your replicated spectra because of the sampled signal through a low pass filter in such a way, the low pass filter is in such a way that you get back the original signal. Is everyone understanding? Has everyone understood the that I could say that the thumbs rule with respect to the sampling theorem? All right. So if I say that my TS is equal to 1 over 2W. So TS is equal to 1 over 2W. So 2W will come the numerator, 2W minus 2W, it becomes W. So W less than equal to W dash less than equal to W. This means W dash is equal to W, which we know that so TS is equal to 1 over W is equal to 1 over 2 TS. So TS W is equal to 1 over 2 TS. So in that case, W dash will be equal to 1 over 2 TS, and that I've just told you here. In this case, you could see here that you are sampling at 2W. Okay, this is the replicated sample. This is the original signal, and then this is its this is its copied version coming at the sampling frequency. So here you can see that your W dash is actually equal to W, because with this you can get back your original signal and it will have no replica of the of its copy coming in this bandwidth. So you will get back the original signal. So but normally we place this replica far apart so that you have a distance, as we saw here, which is most of the times called the guard band, as you will be studying. So in that case, W dash is equal to the half of TS, 1 over TS is a sampling frequency Fs, so it is half of TS. So as you can see here, this in this case only this is half, W is half of 2W, so it is half of TS. So in that case, TS is equal to 1 over 2W, or all that, W dash is equal to 1 over 2 TS. So you can put the W, 2W, and W will become equal to 1 over 2 TS. So TS, this all will cancel. This will remain TS. And again, this will become, 2W will become TS. 1 over TS, this become T over TS, this becomes just N. So this is another simplified form of the interpolation signal provided your T is equal to 1 over 2W. So this was just a thumbs rule explanation or the idea behind the sampling theorem. Now we will go to its mathematical description. So for most of our problems, this thumbs rule interpretation is enough to understand. But yes, we know that once you are studying these courses, you also have to see its mathematical proof. Let us see. First of all, I would like to explain with the respect to the book as is my practice, but then some subtle points not given in the book or from practical sides they will be discussed later. So let us go. First of all, let us say that x delta is my sampled signal. So how do you sample the signal? You just multiply the signal by a impulse train, right? Impulse train, they are defined at the multiples of the sampling interval, all right? And you have an infinite impulse train, you just multiply. So uh, then you know that the signal value will only exist at the point of the impulse, which is at nts. So your sampling will result in the sampled sample scaled by the signal value. This you all know, so we don't have to go into detail. I can also write this as x of t times the sample. Yes, because once this goes inside, this becomes from the shifting theorem, when xt is multiplied with del. So xt will only define at the point of the impulse, which is at nts. So it will definitely become x into nts. So आप ये भी कहें, पहला ये स्टेप लिखें जी सैम्पलिंग में मल्टीप्लिकेशन, और नेक्स्ट स्टेप में ये लिख लें, या इसको लिख के फिर ये लिख लें, एक ही बात है. एंड यू कैन वेरी वेल अंडरस्टैंड. So yes, all right. So we have seen also this thing, except t is equal to this. Now what I do, because you know the inherent understanding of the sampling theorem, it lies in its frequency domain representation. So we have to take its Fourier transform. We apply the Fourier transform of the product of these two signals, and we know that when a signal is being multiplied, then it is being convolved in the Fourier domain or in the frequency domain. This will become x of f convolved with x of f of this whole thing, or the Fourier of this whole thing. Now, Fourier of the impulse train in time, actually it has been discussed in chapter 2, but I would just like to also revise it here. You can also see from there, no problem. So it all starts, that the DC signal, DC spectrum, or the DC signal in time, has an impulse spectrum. It only exists at f0, an impulse, and you can see its proof. Thus we have also done that impulse inverse Fourier, impulse in frequency inverse Fourier is equal to 1, a DC signal. And you can also use other fact that if I have del f minus f naught, this will give me ej2 pi f naught t. This you've already seen. You can also perform like this in same fashion, but you can apply the modulation that if I multiply 1 by ej2 pi ft, then the frequency spectrum will be shifted to the point of the harmonic, which is delta f minus f naught, as we have seen in the previous chapters of analog. Now we have seen if we have any xt, any signal xt, and we know, but let us say it is yes, it is, let us say it is a periodic signal x of t. So I know I can represent my x of t as a by the help of the Fourier series. All right. So that periodic signal can be written as the Fourier series coefficients time the the harmonics, the complex exponentials on the various harmonics kf naught, all right, and then summation. So this is the famous Fourier series representation. You can write any product signal as sum of its scaled sum of its harmonics, all right. So all right, now Fourier of this Fourier series representation, so if this is this, so ejk will be just f minus kf naught, and then summation will also result in summation. So we can very well see that a periodic signal in terms of its Fourier series coefficients can be represented as a train of impulse in frequencies. Train of impulses in frequencies actually represents a periodic signal. This we have also seen and you have seen in your past courses. Now I say that this periodic signal is actually a train of impulse in time, because remember, for sampling you have to multiply this with the train of impulses. So I have a train of impulse and I want to find its Fourier series coefficients. So how can I find its Fourier series coefficient? How can I find its AK or its Fourier series coefficient? Very simple. You just take the signal from within one time period of your signal. So your signal is appearing at 0 ts. So you just take one period. Let us say you take the period from minus ts over 2 to plus t over 2. Interval is ts. Whatever the time period, you just have one impulse with n0 within this time period, and you apply the famous ej 2 pi k f naught, where f naught is a periodic, is the fundamental harmonic, which is 1 over ts. The time period is 1 over t is ts, 1 over ts t. And again you apply the shifting theorem. So the function will exist only at the point of impulse. Impulse is at 0, this will become 0. E of j0 comes out. A square area under the curve of the impulse is 1. So your A of k comes out to be 1 over ts. So you can see that this signal will have this representation with 1 over ts, and that will become an impulse train of frequency at 1 over ts. So you can see here that this is your impulse train. It can be represented as this signal in terms of its Fourier series coefficients. And once these are the Fourier series coefficients, then we know that this is the frequency representation of uh, this train. So you have a train. So a train of impulses results in a train of impulses. A train of impulses in time domain results in a train of impulses in the frequency domain. Oh. So after this explanation, you can go to the book here. So train of impulses in time results in train of impulses in frequency with AK is equal to 1 over Ts. So I just write this Fourier transform in terms of here. So you just write this in terms of the above function, you get this. Now we have to take convolution of S of x in the frequency domain. The convolution has to be taken. So this is again very well known theory. Convolution results in the function at the point of the impulse. Alright, so you have seen this previously, but again many students, they are not able to understand. I have made their notes. You convolve your function. Alright, you convolve your function with this impulse. So what this means? This means x of tau into x of t minus tau d of tau. This becomes actually t. Just for explanation how to do its convolution, x of tau t of minus tau. So after multiplication of a function with an impulse, the function exists only at the point of the impulse. So the point of the impulse with respect to tau is tau, this is 0, so tau is equal to f minus n over ts, f minus n over ts. So f minus n over ts is constant with respect to tau. It comes out. Inside again you have integral of tau, which we all know comes out to be 1. So hence convolution of x of f with the impulse results in the same function at the point of the impulse. Very famous rule. This I have just shown you. That is why convolution will result in this function at the point of the impulse f minus n over ts. So this is your frequency domain expression or representation of your sampled signal. And this is also shown here. Sorry, yes, this was the original signal, and this is the frequency domain representation. This is the frequency domain representation of the original signal, and this is the frequency domain representation of the sampled signals. So you have these replicas going up to infinity. You have minus 1 over Ts, minus 2 over Ts, minus 3 over Ts. You go on and on, and also go on and on like this. And the amplitude will be 1 over Ts. If it is already A, then it will become A over Ts. So this is the same thing which I told you with my notes, and here you can see that this is the frequency spectrum of your sampled signal. Acha. Here, so we have seen this plot that the Fourier transform of the impulsed or the sampled signal, the impulse sample signal is actually the replication of the Fourier transform of the original signal at fs or at 1 over ts, and we have seen this plot. Now what happens if, for example, I say no, my ts is not less than or equal to 1 over 2w, but my ts is actually greater than 1 over 2w. Alright, in other words, you can very well see that I can write this as 1 over fs comes here, 2w comes here, so 2w becomes greater than fs. So fs is less than 2w. This means, if you can very well see, that yours sampled will be somewhere here, and this portion will come inside here. So you will have a aliasing or interference. You can also see this thing. If your if your ts is not less than or equal to 1 over 2w, or you can say fs is not greater than or equal to 2w, in that some portion will be actually coming beneath or behind, hence interpolation. Hence you won't be able to get back your original signal. To get back your original signal, you must satisfy the Nyquist criteria. And if you do not sample at its appropriate uh, sampling interval or sampling frequency, then you get aliasing, which I just showed you. Sorry, this is aliasing, that the replica spectrum interferes with the original spectrum, right? So if you even sample, if you even reconstruct, if you even get this back signal, you will be getting this much signal because of the interference of the other replica. So you won't be able to get back the original signal. So if this condition is satisfied, no problem, there will be no overlap, and hence you can apply a reconstruction filter. So let us say this condition is satisfied. So what should be my reconstruction filter? So again, I've told you the intuition behind reconstruction is that, let us say, to satisfy the sampling theorem, you just try to get back the original message signal. So which I just showed you here, there also, that you just want this portion from minus w to w. So you just want to get back this much signal, okay? And at the same time, you would require that from 3W to W, this must be 0. Reconstruction filter must be 0 so that you do not get any replica. Alright, this is also 0. So from 0 to the sampling frequency, this portion is definitely 0, so you don't get back the original spectra. And while this portion will be taken out by a reconstruction filter. So the condition is that till W reconstruction filter is TS is definitely 0 for frequencies that are greater than 1 over TS minus W. So just told you this is 1 over TS minus W. So frequency is greater than this, the reconstruction filter is 0. In between you could have any choice, but definitely from 0W it must be equal to T, because you know your spectrum at this point we just saw it is 1 over TS, as we saw here. The spectrum is 1 over TS. That is why you multiply it with TS. Okay, so that you know TS cancels and you have get back the original spectrum. So filter has to be TS up to W. From TS 1 over TS and then 1 over TS minus from behind frequencies of 1 over TS minus W to TS, the filter must definitely be 0. In between, that is between W and between 1 over TS minus W, it could be having any characteristics. So yes, so one choice of this filter or this reconstruction filter or this could be an ideal low pass filter, ठीक है, और bandwidth W जो मैंने अभी आपको इधर अपने नोट्स में भी दिखाया था कि this could be one ideal low pass filter of bandwidth W dash, all right, or here you know W dash is equal to W is 1 over 2 or 2W. So this will be its yes, W dash is equal to 1 over TS minus W, and you can see that this W dash satisfies this equation also. So W dash is equal to W here, and you know this was already equal to 2W, this becomes WW, so W dash is actually W. So what will be my reconstruction filter? You can see reconstruction filter must have a width of W, मतलब कि ये you know in representation of a rect. So we this will be a rectangular function in frequency, all right, and its width will be 2W. So we will have a rect like here, like this, and height will be TS. So TS cancels with 1 over TS, and we get 1. We get back the original. So this will be our requirement. So this was my sampled signal. So output of my low pass filter or reconstruction filter is the sampled signal Fourier transform times the Fourier transform of my reconstruction filter. TS is height, rectangle F over 2W. All right. Instead of multiplying, we take it into the Fourier domain. So you know x tilde of f is actually x tilde of t. Multiplication becomes actually convolution, and then you know rect of f over 2w we have seen many times. So sinc of t will be rect of f, and then sinc of 2w dash t will be f over 2w, and also you know uh, this 2w will come also here. All right, we have seen this many times. What is the time domain? When we have seen the sinc of t is equal to rect of f, and if you scale this here, so you have your sinc will be scaled by multiplication, because you are dividing here, so you will be multiplying with 2w here, as well as you are multiplying ts by 2w dash. ठीक है, हाँ जी समझ आ गया ना ये चीज़ यहाँ से किस तरह से आई है? ये मैंने काफ़ी दफ़ा किया हुआ। रेक्ट ऑफ एफ सिंक ऑफ टी है, रेक्ट ऑफ एफ को आपने 2w से स्केल किया तो मल्टीप्लाई भी 2w से करें, और यहाँ भी मल्टीप्लाई 2w से कर दें। ऑलराइट, टी एस तो पहले ही था। ऑलराइट, सो दिस मल्टीप्लिकेशन is actually convolution in time. So I did the multiplication in Fourier in the frequency, because I know that by multiplying the spectrum with this rect of 2w dash, I will just get back my original signal. So convolution, I write the sample signal in this form, and the signal is already in time domain. Now I do the convolution of these two signals. So we have seen earlier in the proof that convolution of an impulse train with a function sinc results in the sinc function at the point of the impulse train. This can be very well proven again. So this will just become, instead of t, this will become t minus nts, and all of this is same. This comes here, and hence this is your xt. So you are getting back your xt by multiplying your sampled signal by a sinc, and then adding up all the sincs, you get back your original signal. So we can perfectly reconstruct the original signal. Sampling rate is 1 over 2w is also in, but generally sampling rate is greater than 1 over 2w or equal to w, and if this condition is satisfied, then there will be no aliasing. This sampling rate is also called the Nyquist sampling rate. And if the sampling is done at the Nyquist rate, that is f is equal to 1 over w, as we have just seen, then the reconstructing filter will have a width of a bandwidth of w dash, or a width of bandwidth of w dash, or w, or bandwidth of w, and hence its width will be 2w. This we already have seen. In that case, you know, when 2w dash is equal to w and 2w is equal to 1 over ts, so all of this simplifies to this thing, as we have also seen earlier. This we have seen. So 2w is ts. You can also write xnts here, sinc of 2W is 1 over Ts, this becomes T over Ts minus, and the same signal that we saw earlier. So we have proven the Nyquist theorem. So now what happens in practice? In practice, usually the sampling is done at a rate higher than the Nyquist rate. All right. So you also put a guard band, which is between 1 over Ts minus W and W, as I have just told you that this is at sampling rate. This is also good, but this is practical, that you sample at a frequency higher than the sampling frequency, let us say 4W. So this range, this region from W3, this will be called the guard band, because this is the bandwidth, this is the guard band, and this is the portion from the replica spectrum. So this will be called the guard. So we have put a guard between the original message signal and its replica, which is now standing at 1 over Ts minus W. This is 1 over Ts, because Ts is here is 4W. 1 over Fs is 4W, so Ts will be 1 over 4W, and this will be 1 over 4W. Yes, 4W minus W, this is 3W, or you can say 1 over Ts minus W. This portion 1 over Ts minus W. So you come here, all right, and this is your guard band between this point and this point. This portion has to be definitely 0. This portion is Ts, and in between you have any characteristics. And this region from 1 over Ts minus W, which will come out to be minus 2W, which is 2W, and 1 over Ts is Fs. So Fs minus 2W, this will be called the guard band. So this is your Fs minus W minus this region will be called the guard band. So this example is very simple. He just is sampling at xt plus t naught. So again, you have just have to apply the sampling theorem. Here he has given that this is the bandwidth, but you also need a guard band. So what you will do, you will multiply it by 2, and then you will add it by the guard band, as I have shown in the notes here. This region is Fs minus 2W, which is the guard band. So guard band is equal to Fs minus 2, hence Fs must be equal to Wg plus 2W. Alright. So if you want to put a guard band, let us say of some frequency, take the double of the bandwidth of the signal and then add a guard band, you will get your sampling frequency. So this is all that has been given in the book. But as I've told you that there were some subtle points which were not in the book, and they were explained very clearly by Dr. Tahir. So I will be also sharing his notes. So no, but I would just like to revise some of the points. So we have seen aliasing. Aliasing will occur if your TS does not satisfy the Nyquist criteria. All right. Or in other words, you can say that Fs is less than 2W, or you can say that Ts is greater than 1 over 2W. Whatever the case, you will have aliasing, you will have interference of the original spectra with the replicated spectra. So what you do, you use a anti-aliasing filter before you pass your signal to the sampler. You put your signal through a anti-alias filter. So by putting the signal to an anti-alias filter, you can very well see that the signal will already be cut at this portion. So even the replica will not be able to cause interference because the signal has already been band limited. देखिए पहले भी band limited था मगर previously its bandwidth was going up to here. ठीक है, so you have this much range. So why don't cut the signal at this point? All right. So in this way, you can very well see that there will be no, interference, or you can say you cut the signal at this point, or you pass it through an anti-aliasing filter. So you can see once I cut this, so this spectrum will end here, this spectrum will also end here, and there will be no aliasing effect or no interference from the replicated spectrum. Now, some of the subtle points with respect to the practical application of aliasing is as follows: that aliasing is not consequence of undersampling. This point can only be explained by a practical engineer, not a theoretical engineer. And again, I am grateful to Dr. Mutahir for giving me this point. So aliasing is a consequence of undersampling because is not a consequence of undersampling. Here we are just saying that aliasing is a consequence of undersampling. We are not sampling at the appropriate interval or frequency, and that is we are getting aliased. But from practically it is not, because remember that the signals that we are dealing in practice, we know they are time limited, and that is why they are frequency unlimited. All right, so they have, once you time limit the signal, then you have various all the frequency components, like this, as you have seen in a rect you have a sink which has almost all the frequency components. So you have already a band limited signal. So if you have if you have unlimited, not a bandwidth limited but unlimited signal, then you have to apply aliasing. Aliasing will be unavoidable, so that you band limit your signal. Once you have band limited signal by passing it through a anti-aliasing filter, then you will sample it at a frequency double the bandwidth of your anti-aliasing filter. So use of anti-aliasing filter is recommended at any sample rate. अब देखिए ना, सिग्नल आपके पास आ रहा है, फर्स्ट करना आप उसमें आप एक्चुअल सिग्नल जो गेट करें उसमें तो हर तरह के सिग्नल ऐड हुए हैं। वैसे भी आपका सिग्नल भी है एक, तो वो भी टाइम डोमेन लिमिटेड है, तो बैंड लिमिटेड, मगर और ही पता नहीं कितने सिग्नल्स होंगे। तो अगर आप उसको किसी फिल्टर से पास कर देंगे तो फिर तो आपने उसको बैंड लिमिटेड कर दिया, वरना तो उसमें हर तरह की फ्रिक्वेंसीज हैं। अगर आप डायरेक्ट सैंपल कर देंगे तो यू विल ऑलवेज हैव द एंटी एलियासिंग। Another point again not given in the book, and I am thankful to Dr. Tahir, is that sample. Now what theoretically we are just saying that we have a train, just multiply the train with the signal and you get the sampled version of the signal, and in Fourier domain the spectrum will be replicated at every other 1 over Ts or every other Fs. Right, this is good. But can we make these 0-bit impulses in reality? No, we cannot have these pulses, and normally we have these rectangular pulses, so they have some width, which is tau. So instead of an impulse train, we actually have a train of rectangular pulses. All right, now so this is the Fourier series coefficient of this train. Actually this we have studied in our previous lectures for chapter 2. A very important part, that what is the Fourier series of the this one. This is again a train of rectangular pulses, same train there, Now it is a tau, it is repeating at t naught. So t naught, is my sampling frequency. The width is tau. So we saw that its Fourier series coefficient will be given as follows. So it will be t over tau sinc n tau over t naught. So that is why I am multiplying my signal not by an impulse train but by a train of rects, and we just saw that those train of rects could be given as follows. So I just write this there. Alright. This will also cover for n is equal to 0, because for n is equal to 0, sinc of 0 is 1, and you will be just getting again tau over ts, because the width in time is 1 over ts. Sorry, the width is tau, and the height is width is tau. All right, and the height is 1 over ts. So you will again get back t, even for n0 you will have tau over ts. So इसने इधर भी शायद लिखा हुआ था, देखे ना. For n is equal to 0, you can very well see that the integration is very simple, and x naught comes out to be tau over t naught. So for n is equal to 0, sinc 0 is 1, you will just get tau over t naught. Because for x0, this will be 0. The area under the curve, we will see, will be tau, because the height is 1. Height is 1, width is tau, so total area under the curve will be tau. Tau divided by t naught, this will be just tau over t naught. So this is a very valid representation which you can write here as the teacher has written here. So this will be Fourier series coefficients. Now multiplying your signal with this sinc train means convolving the Fourier domain of the signal with the sinc train. Again, we have seen earlier that this is the Fourier series representation. So it's Fourier. We have seen the coefficients comes here. Coefficient come here, the Fourier series coefficient, they will just come. पहले आपके पास 1 over ts था, अब ये पूरा का पूरा Fourier series coefficient है. It will just come as it is, and we have seen that this ej and 2 pi over fs actually comes out to be f minus n 1 over ts आएगा actually. fs 1 over ts के बराबर है. This we have already seen. So at an exponential train results in an impulse train. This we have seen in my notes also here. An exponential results in an impulse train. Like this. So we have done till this point. Rest of the, as time is up, rest of that we will be studying in the next lecture. So I hope none of you have any questions. I will stop the recording.